everyone. My name is Alex. I'm an engineer at Interloon, and I'm about to tell you about Interloon's upcoming lunar surface mission, Prospect Moon. So at Interloon, we aim to commercialize the moon's natural resources, starting with helium-3. Most everything we know about helium-3 on the moon comes from testing of Apollo samples and remote sensing data. So with these data sets, we've been able to determine that most helium-3 on the moon is concentrated in mature, ilmenite-rich Mare regions on the near side of the moon, kind of like you can see on the left side of that heat map there. So what do we do with this data? The Prospect Moon mission is going to be going to one of these Mare regions where we expect the concentration of helium-3 to be highest. We'll actually be doing in situ measurements of the helium-3 in the regolith, as well as the other volatiles that are released when we process it. We'll be doing this with a variety of tools, including Interloon's novel regolith processing technology, a mass spectrometer to basically sniff the regolith as we process it and see what comes out, as well as a variety of imagers, including a multispectral imager that can sense the proxies for helium-3 that are remotely detectable in the regolith, kind of up close. So in doing all this, we'll be able to sort of increase our confidence in mapping the moon remotely for helium-3 concentration, as well as getting some really valuable flight heritage on Interloon's processing technology, or software, or avionics, and whatnot. This mission is going to be entirely commercially led, but is going to be launching on a CLIPS-proven lander. So as such, this approach would have been infeasible if it weren't for NASA's investment in CLIPS. So shout out to CLIPS. And also shout out to the NASA Flight Opportunities Program. It's been really invaluable to developing our technology. Lastly, but perhaps most importantly, we have additional payload capacity on the lander we're launching on. So if you have a payload but you don't have a ride, let's go to the moon together. We would love to meet you. Come find us at the poster session. Thanks.
Hello, everyone. So yeah, let me start just with a simple reality. Wireless networks on the moon will be essential infrastructure, yeah, like oxygen, power, like mobility. So yeah, reliability and coverage alone isn't enough in the moon. So on the moon, the infrastructure is always limited. So you can find like interference, lots of problems. So the problem isn't that the systems aren't good enough, but the problem is that they don't understand the situation they're in. So the existing architectures are good enough, so a video stream and a medical alert are treated the same. So while there are automatic configuration tools, they don't always adapt to events or they cannot coordinate. So as a result, astronauts already under pressure may still need to troubleshoot the network. So at the top of the architecture, our solution, we rely on Earth-based assets. So as we move down through the stack towards the lunar surface, we shift to local control. So based on local agents powered by lightweight AI, the system is able to interpret high-level inputs like, hey, relay medical data, or I am in an emergency. So for a real use case, in this scenario, an astronaut during an EVA crosses into a zone with no direct base connectivity. Something goes wrong, and a biomedical alert is triggered. A nearby rover detects the context, recognizes the lack of coverage, and autonomously moves into a position to serve as a relay. The system prioritizes the critical urgent data over all the telemetry. So the network understood, reacted, and supported the astronaut with no delay. So because on the moon, wireless isn't just convenience, it's survival. And we enable the network to automatically understand and automatically behave on behalf of the humans. Thank you.
Well, good afternoon, everyone. Thanks for being here. My name is Marshall Eubanks, and I'm here to describe a product we're unrolling called Ringside Seats. And I think this is a commercial product. It's intended to develop and deal with what is fairly obviously a real problem of lander support. As people know, there's no real GPS on the moon yet. There's no real lander support in the sense of runways or anything like that yet. All of that's going to come, but it's not there now. And so we were thinking about how could we use the tools we have to try and help that now, before all this is installed globally, more or less, on the moon. So Ringside Seats is based on our moat penetrator. Here's an engineering test model right here. This has been fired from a cannon, which is actually surprisingly fun. The first model we had was destructively tested, not intentionally, but it fell apart. So this one is been fired, but it's been fired with instrumentation in it. The instrumentation survives. So basically the idea here is, and one of our original deployment modes was to just carry one on the leg of a lander and just drop it as it comes near the landing. And then we thought, well, what could we do for a lander? And so if you look up here, you can see this is one model. I mean, it's a kind of, I'd love to land on the rim of Giorgio Bruno crater, but probably it won't happen soon. But you would deploy about a minute before you deploy about a minute, you would drop, and it would take about a minute to go down to the surface. It would take that you would get there probably a minute before the lander got there, maybe more. You could land we would land on the surface and have cameras. We could image the lander. We could determine its position. If it's got horizontal velocities or whatever, we could determine that. In any case, we have this as a demo tomorrow. So I'd welcome people to come and take a look at that. Thank you very much.
All right, Alan, are you online?
Yes, I am. Can you guys hear me?
Yep, 2 minutes, go.
Awesome. Thank you very much. Thank you guys for your time. My name's Alan Carter, and I'm with Outward Technologies, and we just want to give you a quick introduction of some of the work that we've been doing in terms of additive construction. I'm sure a lot of you guys know that kind of these lunar missions are going to require some type of civil infrastructure. We're thinking landing pads, roads, building foundations, and construction of those is going to require systems that are lightweight, low power, and minimize process consumables. And so to do that, we are actually developing some concentrated solar energy systems, right? Developing a process called solar selective melting, which requires no consumables whatsoever. I actually have a photo of one of our projects that we're currently working through with an SBIR phase 2 called the Lunar Articulating Mirror Array, where we use a bunch of different mirror facets to form a melt pool on the lunar surface, scan it around in a scan strategy, and produce some of these different horizontal structures. And there's been a lot of research for using concentrated solar energy for these different thermal processes, but we wanted to share some of the research that we've been able to produce in vacuum, right? So here are some of the specimens we were actually able to produce using on-sun testing, showing some of the structures we've been able to do. And some of the results that we've found is it's actually easier to form a melt pool in these vacuum conditions. We need less power density to do these melt pools, though we are fighting phase stability. We're getting these porous structures, but we see some interesting things and are able to control that. So with these concentrated solar systems, we're not carrying a magnetron, we're not cooling a laser. We can produce these systems at a lot lower mass and a lot lower electrical power requirements. So yeah, come find us during the poster session. I would love to talk about more of our results. So thank you for your time.
Hi folks, my name is Joe Church and I'm presenting Lunar Leaper. This is a small mission concept being led by ETH Zurich. You might be saying, why Zurich in Switzerland? So ETH Zurich specializes in legged robotics, and for certain lunar missions we think this is actually an ideal approach to exploring some of this rough terrain. So this mission is focused on exploring a lunar lava tube. Specifically, we're interested in visiting the Marius Hills pit. And we're proposing this vehicle. It's basically a quadruped that uses reinforcement learning-based control for navigating this challenging terrain. We're working with a pretty large international team, about maybe 30 people now and growing. And we just had a MCR level review about a month ago. Right now, we're focusing on TRL development, or TRL maturation of our locomotion hardware. So this sounds interesting. We'd love to talk to you more. We're looking for collaborators and potential missions that we could ride along with. Thanks so much.
Hi, I'm Joseph Cunningham. I'm a PhD candidate at Virginia Tech, where my research focuses on the structural health monitoring capabilities of polymer-bonded regolith composites, where I use a CNT-doped epoxy as a binder material. We're going to go top to bottom, left to right. The first thing you can see in the methods section is a finished composite specimen, including attached electrodes. We test this in the testing setup seen at the bottom there with an Instron uniaxial testing rig, an LCR meter to pass an alternating current through our electrodes, and a custom LabVIEW program to analyze the data and find the outputs in resistance and reactance regimes. Moving on to the center, in the SEM imagery at the top, you can see a zoomed-in specimen of the LHS-1 regolith simulant that I use in my research in an 82% weight ratio for my materials. You can see the angular geometry that's prominent there, and that also shows up in the bottom electron micrographs, which show the fracture surfaces of some of the specimens, as well as some very interesting fractographic features that show the damage propagation methodologies throughout the material itself, which has a lot to do with our response that we see in the sensing effects section. That first graph has a number of different regions noted. Most of those were noted in simulations prior to testing and were experimentally verified. Of most interest are the 2 and 3 regions, which are the linear region, where things follow a Hookean propagation in both the material and the electrical properties. When those things begin to deviate from the linear, we expect that microdamage has begun to occur in the specimen. And eventually, at the end of region 3, we reach a minimum, which corresponds with the strain at max stress. Now, interestingly, depending on composition, there look to be some predictive capabilities of the electrical metrics as they occur before the corresponding material metrics. The bottommost graph shows some sensing of individual damage events through looking at the slopes of the normalized change in resistance and reactance curves, which spike when stress falls dramatically. I'd love to talk to you more about my research at my poster during the session and hope to see you there. Thank you.
Hi, everybody. Thank you. I'm Alex Gilbert of Xeno Power. We're developing commercial radioisotope power systems. Now, you all know radioisotope systems. Plutonium have sent us to all corners of the solar system. But when we're looking at a sustained and large presence on the lunar surface, it's just not going to cut it. It's $500 million plus per unit when you look at all the costs. There's one of them available per decade. And I can bet that as lunar surface users, you're probably not getting one. So Xeno is the vanguard of a large and emerging commercial radioisotope industry. We're developing strontium-90 and americium-241 radioisotope systems. We have demonstrated an actual radiological prototype at one of the Department of Energy's national laboratories. We've secured fuel and facilities to actually produce these at commercial scale. We are on track to do launch approval in 2026 and our first launch in 2027. And the question, I think, really is why? We have a vision that everyone that's heading to the lunar surface can have a radioisotope option. First, for planetary and space science, for everything from very small missions that right now are not getting past the conceptual stage because they do not have these, to very large ambitious missions across the lunar surface, things as large as things like the Lunar Geophysical Network or other New Frontiers class missions. Crewed exploration is something that has historically been directly supported by radioisotope systems during the Apollo mission. When we're looking at Artemis and having a sustained presence on the lunar surface, we want to make sure that our systems are survivable, that you have redundancy, they're able to have many different nodes in a network. More broadly, when you're looking at infrastructure on the lunar surface, you want to make sure to have PNT, communications, large nodes. They need to survive the night. If you actually look, and we ran the numbers, if you look at the surface operational data for going to the lunar surface, 93% of hours on the lunar surface are radioisotope enabled, and I bet you that that number will not be that different in the future. Finally, just as one of our colleagues mentioned, there's a lot of interest in commercial mining on the lunar surface. To do that, you need to have reliable, sustainable energy. So please drop by our poster. We walk through a lot more of these demand types in detail, and thank you very much.
Hello, I'm Brian Glass from NASA Ames, and my colleagues and compatriots and I have been looking at poking holes in things, and this morning you heard some discussions from Steve in the morning panel about drills. Drilling is important on the moon and also Mars going forward. However, the sorts of 1-meter drills that we see, they get into trouble in about 10 seconds, and that makes them okay to be maybe ground controlled or locally on the moon. As we go Mars forward, though, you can look at the light speed time delays and do the math and see that that's not really going to work that well. So the automation and the ability to see faults and problems and avoid the problems on the Mars and going forward is a significant problem, probably an order of magnitude more complexity in software and automation than we actually need for the moon. So we've been looking at this and going to dirty places and sometimes impact craters like you see in the lower right, Houghton Crater in Devon Island in the Arctic, but you have impact heights and fallback breccia and subsurface ice. So if you're looking at things that are an actual analog for the lunar South Pole or for the Mars northern latitudes, it's great. So we go and we try to creatively break things with some of Honeybee's finest. They're an industry collaborator for something like 20 years now. And we will go there probably again this summer. Some results from this past summer, and you see a trident there in the bottom center, actually. We managed to break it and had to take it back to Honeybee for repairs, actually. But as you look up in this chart, you can see a couple of faults, one about a third of the way across that dips that green flat line, hard material, no progress. We tried to extract, we couldn't pull out. We had corkscrewing, a different sort of fault. The software diagnosed, saw that the changes had been detected and responded and got us out of trouble. And we are working on things like change point detection and machine learning, not large language models. Thank you. Bye.
Good afternoon, everyone. My name is Abigail Glover. I recently wrapped up my undergraduate degree at the University of Central Florida, and I'm the current project manager for RIDER, or Regolith Interactions for the Development of Extraterrestrial Rovers. For those unfamiliar with RIDER, it is a large-scale testbed located at the University of Central Florida's Exolith Lab with the ability to operate and observe rover wheels in either lunar or Martian regolith simulants. While the testbed offers a lot more than I'm able to discuss in 2 minutes, I want to chat about all of the upgrades that we've made in the past year since it was presented at LSIC Spring 2024 meeting. So to start off, the team has implemented PID controls and LabVIEW, enabling automated operation of the testbed with the ability to view live data in real time. Additionally, we've added an adaptable hardware suite, which you can see in this middle image here, that was successfully used with the Lunar Vise team to evaluate thermal distribution on the surface layer of the regolith last fall. This also offers a location for people to add sensors and additional hardware at their leisure. Speaking of hardware, we now have an infrared heater available for use with the ability to reach temperatures above 120 degrees Celsius. We've also added additional higher wattage lights for variable testing conditions. And in addition to the currently installed Ardu cams, we now have a GoPro Hero Black 13, which has the ability to capture up to 400 frames per second at 720p or 120 frames per second at 5.3K. I could go on and on about all RIDER has to offer to the community, but if you'd like to chat more, I'll be presenting at the poster session, or if you'd like to reach out, our email is available here. With humanity looking to go back to the moon and beyond, we need to make sure our hardware works here first, so let us help you with that. Thank you.
Hey everyone, my name's Mark Hardigan. I'm a PhD candidate at Georgia Tech under Dr. Glenn Lightsey, and I have a poster outside talking today about the measurement and navigation performance for users of a LunaNet compliant constellation. So as some of you may know, NASA, the ESA, JAXA have been collaborating on this shared concept for a lunar constellation that would provide communications and navigation to the lunar surface. The result of this collaboration has been LunaNet, which is an interoperability specification that details signal formats, definitions, and requirements so that realizations of these constellations can work collaboratively for the end user. And realizations of this system for LunaNet will be broadcasting, in part, signals that look like GPS that users can collect with a radio receiver and make measurements off of. So the work I'm showing here is the result of an end-to-end simulation pipeline we've created to characterize the end-user navigation performance. In the result on the poster, it's a lunar lander, but we're also considering autonomous rovers or astronaut EVAs. So the pipeline is generally simulating a constellation of satellites. We're considering the clocks they're carrying, their orbit determination, the transmission hardware, and then we look at all the errors that stack up in that signal generation to reception pipeline and apply those to the pseudorange and Doppler measurements that the lander's receiver will be making. And then all of that gets synthesized inside a Kalman filter to provide real-time navigation to the lunar lander as it's descending. So if you're interested in hearing about the results or learning more, I'd be happy to talk to you at the poster. Thank you.
Okay, hello, my name is Samuel Wright. I'm a graduate student at the University of Louisville, and I was involved in some research involving in-space manufacture of carbon nanotubes. Some applications of carbon nanotubes, they can include like construction, nano reinforcement for construction materials, as well as uses in electronics like batteries and sensors. There's also an application we heard about just recently. So you can use them for a lot of things, and the way that we're going to synthesize them is using methane gas, which is an organic waste material, as well as lunar simulants, which have iron nanoparticles in them. So when we excite the methane gas to a plasma state, the carbon will react with the iron nanoparticles, and they start to grow the CNTs. And we did this on 4 different types of simulants. So we did it on the we did 2 types of simulants in 4 different conditions. So we did Johnson Space Center simulants, as well as the Colorado School of Mines simulants, and we did them in the as-received conditions, as well as when we added extra iron nanoparticles to them. And in all 4 tests, we found that the CNTs could grow from them. You can see the microscope images from them. There's like tube-like structures growing, and from the EDX images, there's the red shows the carbon, and the green shows the iron. So you can see that the carbon is kind of growing from the iron. Also, from the Raman spectroscopy tests, we found that they were multi-walled carbon nanotubes, which have a little bit different properties than the single walls. But if you would like any more information, we have a poster on it outside, so thank you.
Hi folks, my name is Isabel King. I'm an engineer at Honeybee Robotics, and I was also an operator on our Trident drill that was part of the Prime 1 mission just recently in February, March, which is obviously on the IM-2 lander. So obviously we all know that landed on its side, but we were lucky to be on that top panel. And as such, we were able to demonstrate all of the functionality of our drills. We were able to use every motor, and specifically all the steps that we took we rotated and hammered the auger. You heard earlier today, it's a rotary percussive drill, so we were able to demonstrate that capability. We also released our launch locks, which is obviously super important. Without being able to release those, we wouldn't be able to drill into the ground. And with those released, we were able to deploy our 2 linear stages. The first linear stage brings our foot pad to the ground, just typically how we would get stable so we can actually drill into the ground. And then the second linear stage has our actual auger traveling up and down along it to advance into the ground. So at the end of this sequence, we were kind of in the position that we would be in at the end of drilling to a 1-meter depth. And so in addition to those operations, we also had nominal avionics performance. We captured all of our thermal data, and some of that thermal data also included temperature sensors that we have in the auger that could measure subsurface temperature. And so we're very excited that we were able to demonstrate all of this capability on the moon. And I think of particular interest, we were able to demonstrate this in a dusty environment. So you can see I'm calling out here that we have images that are taken from orbit. You can see all of the hardware is pristine and clean. And then the image that the unforgettable image from the moon, you can see that there's dust all over a lot of surfaces. It's particularly visible on those white surfaces, so the Nokia radiator that you heard about earlier, and M-SOLO, which is the mass spectrometer that we were delivering to. So we're very excited for this opportunity. Right now, Trident is already integrated on the Viper vehicle, so we're eager to follow the progress that happens there. Thank you.
Hi, I'm Joel Olson. I am presenting today in place of Dr. Andy Meyer, who was unable to attend. In December of last year, a team comprised of both representatives of NASA's Kennedy Space Center and Lunar Resources performed a demonstration of a Lunar Resources molten regolith electrolysis reactor in thermal vacuum at Kennedy Space Center. This test first melted and then performed electrolysis on 25 kilograms of lunar regolith simulant and was able to perform electrolysis and recover pure oxygen from that. So one of the things that we did was we recovered the reactor afterward, let it cool, and then with the help of a very talented machinist, we were able to actually cut a core out of the melt, and that is a picture of the core up on top there. We performed numerous different analyses on this, and we were able to determine a few things. You can see the results up there. It was fairly porous, as you might expect. A lot of bubbles in there, partially due to the oxygen generation. We determined densities. One of the interesting things was we observed the electrode material throughout. So these are some interesting results, and if you want more information about this, actually my colleague Lucy Somerville and myself are manning 4 posters today, 33, 34, 35, and 36. Also, I need to mention that this was supported by STMD's Game Changing Developments and SBIR, and involved 4 different research labs at KSD. Thank you.
Hello, I'm Ben Nowak, CEO and co-founder of Reflect Orbital, former SpaceX, a bunch of startups, and YouTube. And I'm here to introduce to you Reflect Orbital. The original idea for this company came from looking at all the 1 or 2% increases you get in photovoltaic efficiency and how big of a deal that is for the energy sector. And I remember one day realizing that if you move a solar panel from Germany to Africa, you can increase the output by 300%, 3x it. And if you could also get sunlight at night, you could do another 3 or 4x increase in the amount of power that that solar panel delivers on average. And I just remember thinking about this and kind of looking into the technology a little bit. And as I had worked at SpaceX, I knew that the rockets were there. And if you could just figure out a way to do this economically, it could be a gigantic market. And what we're doing is we're building large heliostat satellites that are very similar to solar sail vehicles, but pulled a lot tighter. So here's just a small mirror made out of Mylar. Obviously, it's quite reflective, and you're able to get a lot of power to the ground. And we're currently building up large rollable tubular members that'll hold about 1,000 pounds in compression. So we have the specularity down, and we raised about $28 million over the last couple of years, and did an application online where we got 264,000 applications for our sunlight for terrestrial applications, so large-scale lighting applications, large-scale energy applications, mining. We can light up anywhere on Earth in under 30 seconds. So we're serving all of those markets here on Earth. But we also have a lot of applicability to the lunar surface. Obviously, we have the ability to reflect sunlight down onto the dark side of the lunar, the dark side of the moon. And particularly the poles are interesting. If you have a constellation of about 80 satellites, you can provide constant sunlight at the north or south pole. We're looking at about a 30-kilometer orbit right now. If we could go a little bit lower, it'd be great. But with a 3,000 square meter reflector, you can get 25 watts per square meter at that altitude. And if you're able to fly as low as 11 kilometers, you get 200 watts per square meter with that same fairly small vehicle. And it's the same heliostat that we're building for terrestrial applications. So yeah, we're looking at launching soon and delivering some power. So thank you.
Hello, everyone. My name is Paulo. I am Volta's Space Technologies CTO and co-founder. For those who don't know us, Volta is planning to build a commercial power utility around the moon that entails delivering power from lunar orbit down to the lunar surface using lasers. Power from lunar orbit has several advantages in that it can be very flexible, very scalable, and affordable, as you don't have to land your infrastructure on the surface. But for missions to make use of this capability, we must solve for reliability and ease of acceptance. We want power to be predictable, consistent, and easy to access, both financially and technically. So to access power, you need a laser receiver, and a receiver that is small enough to fit on upcoming lunar missions, and it is able to cycle through multiple day and night cycles or inside PSRs, potentially under lunar dust. And so Volta, as a prototype that complies with wide temperature-induced thermal stresses in cycles, and that converts at 50% efficiency at room temperature, that retains a conversion efficiency of 40% down to 80 Kelvin. And we're going to have more environmental test results by the end of this year. Then the other things that you need to have is a high-power laser that's powerful enough that can operate into lunar space, and that's a challenge. Volta has built a 600 watts optical output laser that has undergone all the environmental tests. It's the LSIC, and it's currently manufacturing a 1.8 kilowatts laser that's bound to be qualified later the next year. And then when you have such a small receiver, you need to be very good at pointing. And in order to achieve that, we're developing a closed cubic loop system between receiver and transmitter, where the transmitter in orbit has some fine beam steering capabilities and can cooperate with a commercial small satellite deployed in a 100 kilometers low lunar orbit in order to meet those requirements and control the beam displacement on the ground just within a handful of centimeters. So these are the premises on which we're trying to build and deliver that reliability and consistency for power. I'll be very happy to talk more about that with you all later. Thank you for listening.
Hi everyone, I'm Mahek Sarang. I'm the Director of Industry Integration at the Open Lunar Foundation, which is a global nonprofit that's dedicated to the sustainable and peaceful exploration of the moon. Today, I'm excited to introduce a flagship project for Open Lunar, a registry of lunar missions and objects that will launch later this year. As lunar activities scale, we're seeing a greater need for coordination, which is why forums like this exist. Specifically, the steady rise of commercial lunar activity requires new norms for information sharing. In the past, governments established rules through bilateral or multilateral agreements, like the intricate network of agreements that governs the International Space Station. However, this new era of exploration includes a diverse set of actors, including private corporations, state actors, and nonprofits that exist in countries all around the world. We could wait and see which regulations emerge, meanwhile operating in an ad hoc, fragmented manner, missing out on collaboration opportunities or facing disruptions during critical operations. Or we could proactively design and adopt the norms that we want to see that could enable greater collaboration and opportunities for all. A lunar registry serves as a logical first step in establishing these norms, and Open Lunar is building it. It's a neutral, voluntary, and transparent platform that centralizes mission data. Imagine it as an open database that enables lunar mission operators to register and access information about mission plans, landing sites, and even planned activities. A lunar registry could enhance coordination during mission planning, it could increase transparency, and help those outside the industry understand what makes a mission credible and who can be trusted as responsible actors. After an exhaustive stakeholder assessment with over 200 individuals from governments, academia, and the private industry, Open Lunar has begun designing this platform. Our effort complements existing international agreements such as the UN Registry and the Artemis Accords, and Open Lunar is a permanent observer of the UN Committee on the Peaceful Uses of Outer Space. Our process is also designed to ensure that the lunar community shapes these norms, meaning that we will ensure the registry remains completely voluntary. We want to collaborate with the LSIC community to build this registry. This is just the beginning, and we hope that you will help support the future of a collaborative lunar exploration with us. Thank you.
Hi, I'm Chris Stiles. I'm a scientist here at the Applied Physics Laboratory, and as we've heard many times, we're heading back to the moon, but this time for a sustained presence. But launching everything from Earth for that longer-term vision is prohibitively expensive. So our approach is to make what we need, where we need it, with what we have, or ISRU, the core tenet thereof. We started by unlocking decades of lunar sample data consisting of detailed mineral and elemental maps tied to locations, but locked within hundreds of papers. To access this knowledge, we built a LLM-powered intelligent retrieval augmented generation system that extracts geological and chemical compositional data with high accuracy. That data then defines the in situ manufacturing constraints for a given site on the moon. We fed these constraints into our closed-loop materials discovery framework, targeting materials optimal for mission-specific requirements through this predict, make, and measure loop. We're able to target optimal materials for these missions. And that starts with generative AI. Our generative AI creates crystal structures based upon these elemental constraints. And then we use other models to predict their ultimate performant properties that will allow us to achieve these missions. Then, based upon those predictions, we make materials using directed energy deposition at first a small scale and then larger scale to evaluate the feasibility of manufacturing these materials on the moon. Finally, we characterize all of that data and feed it back and learn again and again. Happy to chat with you more.
Hi, good afternoon, everyone. I'm Grace Gao. I'm a professor at Stanford University. I lead the Navigation and Autonomous Vehicles Laboratory, or NavLab. My students and I have been working towards robust 3D lunar surface mapping and autonomy. We know that the lunar surface is quite challenging for autonomous navigation because it has uneven and unknown terrains, harsh lighting conditions. It also lacks features, or sometimes it's hard to have diverse viewpoints. So we have been very fortunate to be able to participate in the NASA Lunar Autonomy Challenge. And then really big shout outs for NASA to provide this autonomy challenge for the community. So we have been working on the perception as well as the simultaneous localization mapping, or SLAM, for this Lunar Autonomy Challenge. We have been using different AI machine learning methods for different elements in this, for example, scene segmentation, such as segmenting rocks, lunar lander or the sky, and from the input images and video, and then things like feature tracking. In addition, we have been leveraging the recent advances in computer vision and computer graphics about neural radiance fields, and then we have been trying to create this radiance field mapping. This is basically a neural network representation of the 3D surface environment of the moon. And then we can utilize this 3D model of the moon surface to generate photorealistic rendering of the scene from different post images. And then we can use this to do better autonomous navigation of the rovers of the moon. Thank you very much.
All right, next we have online speakers. Deborah, are you on?
Yes.
Perfect, go for it.
Hello, everyone. My name is Deborah Esserman, and this session or this lightning talk would be about the development of volatile monitoring oxygen measurement system, what we call VMORMS. This technology was developed for what Dr. Joel Washington mentioned, the molten regolith electrolysis project, where we performed electrolysis on 25 kilograms of regolith. The technology was developed to support it to help in evacuation stage of the reactor, the heating phase, electrolysis phase, and then post-electrolysis. The main aim was to, one, quantify the amount of oxygen that was produced during electrolysis and also detect other volatiles that was produced during the heating phase and electrolysis phase. The technology went through different series of testing before it got to where it is right now. So we'll be having a poster session. Dr. Joel already mentioned it. 3 poster sessions related to the multi-regolith electrolysis test that was performed here at Kennedy Space Center in the GMRO lab. One will be dealing with the core, and then we'll be having the VMOMS, which is mine, as well as a cryptometer test similar to it, and using of the assist chamber for the MRE testing. So beneath the poster, you would see an RGA result of the interesting gases that was detected both during the heating phase and electrolysis phase. We modified our system to include argon dilution at a certain stage during the test. All of this will be talked about. If you want to know more about the results and everything exciting about MRE, do well to pass by our poster session. Thank you very much.
All right, next online, Aileen. Eileen, sorry. Oh, oops, that person.
All right, this is Eileen.
Go for it.
I am great, thanks. I'm a geologist and principal investigator for the Heimdall camera system, launching on Eclipse mission in 2028 to visit Gruithuisen domes. In our team's efforts to prepare for this mission, we've looked at ways to assess angle of internal friction. Why? Because it is a primary variable feeding into loss of traction, and our experience with larger off-world wheeled vehicles tells us that loss of traction can be difficult and in some cases, a mission-ending scenario. The trouble is in acquiring an estimate for angle of internal friction, or phi. It is expensive in resources and thus funds to test in situ, and the regolith samples we have on hand don't cover the breadth of regolith types that may occur in scientifically and geotechnically interesting areas, and Gruitizen is actually one of those areas. So reference materials aren't always adequate either, and testing on reference materials also has the difficulties inherent in testing outside the lunar environment. Experiments in the 60s suggest that angle of internal friction is about equal to angle of repose, which is shown on the right and usually noted as theta, and that should be a theta in this figure, so you can hopefully get the math right. That is, angle of internal friction is about equal to angle of repose for consolidated materials, but greater than angle of repose for loose materials, where both sliding and rolling are important. This means that angle of repose is a conservative estimate that we could design to, and luckily is far more straightforward to assess, needing only a scoop of some type to dump your regolith and a camera to assess the angle between the side of the pile and the surface. If you have any questions, please email me or see me virtually at the poster session. Thanks.
All right, next, Richard, you are set to go.
Hey, my name is Rich Reber. I am a robotic systems engineer here at NASA's Jet Propulsion Laboratory. I have a utopian vision of what the moon will look like, where all of our different robots work together and cooperate to contribute to the collective goal. And the only way our robots can work together is if we have interface standards. So under the umbrella of logic, what I propose is that we start working on an interface standard for robotic arm to end effector interfaces. So there's no standard here, and this is really discouraging to commercial growth and limits our interoperability. So I want to empower, like the best shovel company to make just the shovel and have that be able to work with any robotic arm we send to the moon. Allow things to be commoditized, allow economies to grow, and enable small businesses to kind of get in the game. I came up with some notional standard classes of different loads and different power supply and data rates and position accuracy, just to give us a working point to start from. This isn't a new idea. MDA is working on the clamp interface, which is what they've got. Gitai is their inchworm robot with a similar grapple end. So the idea is to take these ideas, let's turn them into a real standard and start letting industry run with it. So if you want to get involved, I got this little Google form. Literally, just give me your email address, and so we can start figuring out who wants to work together, and we can have a little sidebar, a little workshop, over Teams or something to kind of figure out the next steps. So that's it. Give me your email, and we'll start from here. And that's all I got. I'll be at poster session if anyone wants to chat.